For the next talk, we will hear about how to get together lasers and dark matter. So our speaker for the next round studied physics in Hanover and taught astronomy in remote places like Tanzania. He's a postdoc at the University of Florida, where he now works on the ALPS instrument or device that he will talk to you about, and will maybe give you the chance to one day actually know that at least where the dark matter is that you might want to own. So please welcome with me Simon Barker with Eavesdropping on the Dark Cosmos. Give a warm applause.
Thanks. Whoa, hi. Thanks for having me. Thank you for being here. And did you know that the screen behind me has 2 million pixels? Let's say, just for fun, let's assume this screen is all there is in the entire universe. So if that was the case, this screen would be dark for 95%. 95% of the screen would be completely invisible. There would be another like 85,000 pixels, which are utterly boring. Then we have some cool, like 10,000-ish pixels, which are made of stars. That's nice. We have elusive neutrinos making up like 6,000 pixels. And do you know what the small portion down there is? 622 pixels. That is you, that is me, that is this planet. This is all the higher elements like oxygen and carbon, like gold and plutonium. That is all there is of matter we care about, usually. Astrophysicists care about a little bit more, so they don't care about 0.03%, but more like about the 5% over there on the right. I myself care about the 95%. So I'm interested in the stuff you can't see, in the invisible dark part of the cosmos. So welcome to Eavesdropping on the Dark Cosmos. I'm here on behalf of the Max Planck Institute for Gravitational Physics in Hanover and the University of Florida in Gainesville, United States. My name is Simon Barker, and before I continue to talk about the dark side of the cosmos, I would first like to explain to you what I mean when I talk about cosmos or universe. What is our universe? So I'm pretty sure you've heard that our universe started in a Big Bang, and here we have the size of the universe over age. It took 380,000 years after the Big Bang for the universe to expand to a size where the density was low enough so that light could pass through the universe. So the very first events we can observe happened 380,000 years after the Big Bang. Since then, 13.8 billion years have passed, and the universe became quite bigger. Actually, the universe right now has a radius of 46 billion light years, so a diameter of 92 billion light years. And now you may wonder, how could we see something 46 billion light years away if the light had only 13.8 billion years time to travel? Well, back then, when the light originated, like 380,000 years after the Big Bang, the universe was much smaller, actually just like roughly 40 million light years across. That's when the light from the edge of the universe started to travel towards our point in space. And the universe expanded during the time the light tried to reach us. So it's like the mouse on the rubber band pulling apart. And it took the light 13.8 billion years in order to basically cross 40 million light years. And the universe expanded since then to 92 billion light years in diameter. So that's what I speak about when I say our universe, or more precisely, my universe. I am in the center of this universe. If I moved like 5 meters to the left, my universe would expand 5 meters to the left and contract 5 meters to the right. So you all have different local universes around you. And of course, there are universes out there far, far away with like aliens in their centers, which we could never reach, which have no causal connection to us. We can't see there, we can't interact there. It's universes of their own, but they are in our space-time continuum. It's nothing strange, it's just too far away to be counted as part of our universe. Anyways, our universe looks like that. We can do pictures of it. We can see that there are billions and billions of galaxies out there. Can we? Yes. Billions and billions of galaxies. Each galaxy contains billions and billions of stars. It's a huge space. We can see planets and nebulae. We can see jets emitted from black holes. We can do pictures. But actually, that's all we do. All we know about the universe, as it looks like, we know from light, electromagnetic radiation. That's all we can do. These are the Maxwell equations. They describe light. So one solution of the Maxwell equations is the differential wave equation, which in the end results in periodic oscillating electric and magnetic fields. That's what we call light. That's an electromagnetic wave. And we use this on Earth as well. We use it to see each other. So a light ray, an electromagnetic wave, will bounce off stuff. Different materials only reflect certain frequencies of the electromagnetic wave. And then we receive this wave with our eyes and interpret the different frequencies as colors in our brain. So different colors are nothing but different frequencies of this oscillating field. But again, all we know about the universe, we know from light. Wouldn't it be nice if we could not only see the universe, but also hear it? So we need all these different spacecraft in order to cover the entire range of electromagnetic waves there are. But there's no way to listen to events happening out there in the cosmos. It's all still just electromagnetic radiation. So how could we listen to the cosmos? Here on Earth, we listen through pressure waves in air. So sound waves travel through a medium. Do we have a medium in space? No, in space no one can hear you scream. That's a problem. We can't transmit sound through space. But don't we have another medium out there? In fact, we do. Since 100 years, we know from the Einstein field equations that there is something called space-time. And the Einstein field equations told us that gravity is nothing but a curvature in space-time. So you have a massive object, and this massive object is curving space-time, and then smaller objects do nothing but falling into the curvature of the space-time, this bent space-time. Like here on Earth. Earth is curving space-time, and I'm falling into the curvature of space-time. I'm attracted by the gravitational force of the Earth. That's what I feel. But in reality, it's just curved space-time. So we know there's space-time everywhere, and space-time can be curved. Can't we transmit waves through space-time? Well, we would have to see if these equations, the Einstein field equations, have wave solutions. Yes, they have. And then we would need to find conditions under which astrophysical sources could emit gravitational waves. So what does a star have to do in order to emit gravitational waves in the fabric of space-time? Some years ago, we did some YouTube videos basically exactly about that. Like, what does a star have to do in order to emit gravitational waves? And, well, just listen to YouTube for a second or so. Yeah.
Normally, we would have to solve the calculations involved in Einstein's theory in order to understand. It says that for a system to emit gravitational waves, it only needs a non-zero third-time derivative of the quadrupole moment of its stress-energy tensor. Funnily enough, this is a bit complicated to intuitively understand.
Yeah, that's a math. So you have the stress-energy tensor, which basically describes energy and matter. And if the third-time derivative of this quadrupole moment of the stress-energy tensor of the Einstein field equations, if that is not zero, then there will be gravitational waves. Easy enough. Actually, it is. The picture I can give you is very easy to understand. All we need in order to have gravitational waves are accelerated objects. Massive objects that maybe two stars in an orbit. or basically also me spinning. I'm accelerating my hands in a circle. This is steering up space-time. That's a non-zero third-time derivative of the stress, and so on and so forth. And these gravitational waves are transmitted throughout the entire universe. And there are lots of objects out there that are constantly accelerated. So let's take two galaxies colliding, merging, two supermassive black holes and their centers. Two black holes colliding, huge amounts of matter accelerated rapidly. You have smaller stars or small black holes, neutron stars, falling into supermassive black holes. Of course, this is accelerated matter producing gravitational waves while they fall in. You have very tight binary star systems so close together that the companion star is actually sucking off matter from its bigger one until it explodes, like huge supernova explosions, accelerated matter again, should produce gravitational waves. And yeah, you may have like artificial sources of gravitational waves. Spaceships accelerated very fast should produce gravitational waves. All that I just shown you is not science fiction. No, wait for it. We see rapidly spinning neutron stars, pulsars. We see these vampire stars. We can track the orbits of stars circling around supermassive black holes. We see supernova explosions out there, and yes, we even have a theory on how to build a warp drive. We cannot do that now, and we are not even sure if it's actually possible, but this is the only way we know that could propel a spaceship faster than the speed of light that is not forbidden by physical laws, and that is pretty cool. And it involves an artificial curvature of space-time and some negative energy, but that's just a technical issue. But we know that if a spaceship would enter this warp bubble, it would produce gravitational waves. So when we would detect gravitational waves, we could at least say no. No one out here in our universe is using warp drive, so maybe it's not possible at all. Or we could detect, like we have a warp drive detector now, if we have a gravitational wave detector. Let's see. So, how actually can we detect gravitational waves? The biggest effect of gravitational waves on us is a change in distance. You're sitting there where you sit and you don't move at all, and let me stand over here and not move. And now a gravitational wave is passing through the Earth. What it does is it periodically changes the distance between us by stretching space-time between us and compressing it again. So you don't move, I don't move, but our distance is changing periodically. That's a weird concept. But now we know how to detect gravitational waves. All we need to do is measure distances. Like really, really exactly. The big issue is that if a strong gravitational wave hits our solar system, then the distance between Earth and Sun will change by the fraction of the diameter of an atom. And that's like distance between Earth and Sun. So that's what we need to do. That's how precise we need to become. We need to measure the distance between Earth and Sun with the precision of one atom. Technical issues. We actually solved them. So, okay, maybe let's start first with what we expect to detect. If we could measure that, if we could measure the distance between Earth and Sun by the diameter of an atom, and then amplify the signal and convert the frequencies to audio waves, we could listen to the universe. We could listen to stars exploding, we could listen to black holes merging. And I brought some audio files of like artificially generated signals that we expect to hear. Pulsars are rapidly spinning neutron stars, and they steer up space-time at a constant motion, should just be a sine signal. So that's our sine wave. No. Here we go. That's a pulsar. These are supernova explosions. Can we turn this up a little? Make it louder? Yeah. Pulsars, supernovas. Then we have binary stars in our galaxy orbiting each other. So many of them that they will contribute to a noise floor. We have binary stars that merge and collide. Gone there. And this could even happen with more massive objects like two black holes orbiting each other at low frequencies, coming closer and closer, and merging. Another one. That's what we expect to hear. And then we have smaller stars falling into supermassive black holes. And this is more of the really fascinating signals with lots and lots of details to it. There's another one. You can hear the spins aligning. You can pull out so much physics out of these signals. You get the masses and the orbital velocities and all of that out of these weird noises from the universe, if we could detect them. So let's detect them. We did build gravitational wave detectors. We actually started 10, 20 years ago building these. The two biggest ones are currently in the United States, one in Louisiana, one in Washington State. And that is LIGO, the Laser Interferometer Gravitational Wave Detector. And basically, LIGO consists of two big lasers at a rectangular angle, 4 kilometers long. And when a gravitational wave hits the detector, the distance of one arm, or the length of one arm, will become longer and the other one will become shorter. So all we need to do is to measure the length of the two arms in order to detect gravitational waves. With only 4 kilometer long arms, we need to do that better than the fraction of an atomic nucleus. That's why it took us 20 years to build this thing. And then, last year, September 14th, I guess, need not go too far away from it. Here. Last year, September 14th, gravitational wave hit the detector. So what happened was, we are measuring the length of both arms with lasers. We are sending one laser beam to a beam splitter, reflecting it back from two mirrors, and usually, we don't have light at the output port, but when the gravitational wave changes the length of both arms, we see a light flickering at the lower output on our photodetector. So all we need to look for is this flickering light. And since full brightness and no intensity at all is only like half of a wavelength, so only 500 nanometer in distance, and we cannot only detect full brightness and zero, we can detect a little brightness as well, we can go all the way down to the fraction of an atomic nucleus in measuring the distance variations between the both arms. And then the gravitational wave came, like basically a day after we switched on the device after a big upgrade. A very beautiful signal. And here it is. This is real, this is no simulation. That is the very first gravitational wave ever detected by a gravitational wave detector. You see, it wasn't me, it was thousands and thousands of physicists working on this thing for 10, 20 years. But it's an amazing discovery. We know that the prediction of Einstein were real. What we have here is time over amplitude, and you see that this gravitational wave we detected only lasted for 200 milliseconds. You also have the frequency plot, so the peak frequency was like 250 hertz. That kind of means that the two objects orbiting each other, producing this gravitational wave, had to orbit each other 250 times a second. That's fast. We don't do this around sun. We can also change the pitch of the signal a little to make it. That didn't work. Sorry. Back. One more. We can change the pitch a little, make it easier to hear, and then you can download all the raw data from the Open Science Center. They also provide Python scripts for you, so you can get the raw data and play with it a little, make it sound cooler. Many people did music with it, actually. That was surprising. Doesn't sound that good. But what we can do from the data, what you could actually do with the raw data, is figure out what kind of objects exactly emitted these gravitational waves. So they somehow shielded this thing. Here we go. So what we found out was that these gravitational waves were emitted somewhere from the direction of the Dorado constellation, 1.3 billion light years away, by two black holes, one 29 solar masses, the other 34 solar masses, 36 solar masses. And then again, we only caught the last orbit. So this is real time here. Two black holes, more massive than our sun, orbiting each other 250 times a second and producing one giant black hole. LIGO is actually tuned to detect these high-frequency gravitational waves. That's not surprising because on Earth, everything is shaking at lower frequencies. So let's take a car, or me walking, that's a hertz. So I'm shaking the ground floor with a hertz. A cloud moving over the detector is like a few millihertz, attracting one mirror by its gravity and then pulling it to the other direction. So all the noise sources here on Earth, ocean waves at the shore, are covering up all the gravitational waves we could detect at lower frequencies. So all the stuff which is slower out there in the universe, we could never detect on ground. And like in classic astronomy, what we can't measure on ground, we measure in space, where there are no cars, no waves, no clouds, no me walking. And that is a LISA mission. So the actual proposal for the mission concept is due in January. So we are writing the mission proposal right now. And LISA consists of 3 spacecraft. They will be launched before 2034, like 2030, 32-ish. And they will build a giant laser interferometer in space. It's like playing Star Wars. You have 3 spacecraft separated by millions of kilometers, sending lasers back and forth and doing the very same thing LIGO does. They measure the distance between spacecraft. And if a gravitational wave passes the constellation, the distance changes without the satellites moving. And we can detect gravitational waves, this time at much lower frequencies in the millihertz range. And the entire constellation is so big, like 2 times, 3 times the diameter of the sun, that we can't have it in Earth's orbit anymore. It's trailing the Earth on an orbit around the sun. And you see it up there. If you want your name to be listed on the official mission concept proposal, just visit this website, fill out the information like name and your affiliation, press enter, and your name will be next to names like Stephen Hawking, who's already supporting us. So that's a historic chance to have your name at this ESA document. That would be nice, and we would appreciate it very much. Thank you. Why do we do all that? Why do we want to detect gravitational waves? Well, gravity is the dominating force in the universe. Gravity is cool because it's everywhere. It's not only in stars and neutrinos, it's not only in the heavy elements. Gravity is not only emitted by like the free helium and hydrogen in our universe. That's the 5% of normal matter we can see. Gravity is also emitted by dark matter, stuff we cannot see. Dark matter is completely invisible to us, but we know it is there because it does emit gravity. If you look at the Hubble deep space, that's an image taken by Hubble, and you see all these galaxies. You also see distortions, like these rings, these arcs, as if someone put a lens in front of your picture. This is gravitational lensing. These are strong gravitational fields, like curvatures in space-time, where light is like curved around this gravitational field. And then you have these ghost images of galaxies which are actually behind the gravitational field, now seen as arcs. And by doing data analysis on these pictures, we can calculate the amount of gravity in our universe. That's easy. Then we can also count the dots and get an estimate on the matter in our universe. And then we find out that it does not add up. there's much more gravity than there's matter. So the very easy solution is, well, there must be some matter we can't see, some invisible matter. And this is not the only hint we have that there must be more matter than we can see. Vera Rubin detected by observation that spiral galaxies do not rotate as they should. Like you can calculate the outer star orbital velocity from spiral galaxies, how they should be on the left-hand side, but they actually rotate like they are shown on the right-hand side. And you can only reproduce, like theoretically, the right-hand curves by adding more mass to your galaxy. So spiral galaxies must be much heavier than we see they are. So there must be more invisible matter in there. Again, there's more gravity than could be explained with the matter we see. So we have no idea what dark matter is yet, but we have many ideas. One idea is there's a theory that says there could be an interaction between photons, normal light particles, and virtual photons from electric or magnetic fields. So you have a strong magnetic field, there are virtual photons in there, and you have a normal photon, and these two photons may sometimes, on off chance, interact and produce something we call axion or axion-like particle. And these axion particles would have like very similar properties than what we expect from dark matter, like they don't interact with anything else. And all we need in order to detect them is another strong magnetic field, so these axions oscillate back into photons, and then we can detect the photons. They're like these solar axion telescopes out there already. What I'm working on right now is another project. We are building a dark matter generator. So this is ALPS. It sounds really cool, and thanks. Again. There are many, many physicists working on this. It's constructed in DC, in Hamburg, but I'm actually working in Florida on that, so it's all international. We are on 100-meter time scale, we are building a vacuum system with strong lasers and really strong magnetic fields, superconducting magnets, and we want to have exactly this interaction between light particles and virtual photons in the magnetic field. Our laser cannot escape the generator, but the dark matter, if it's generated, can, and will enter our recombination cavity. Same device, same magnetic field, same properties, same resonant cavity, but this time no light at all. But if a dark matter particle enters there, it is perfectly matched to the cavity and would oscillate back into a light particle, and then we can detect the light. And when we switch off our generator and don't see these light particles anymore, we know what happened. We detect the dark matter, and in the first place, we generated it. This project is hopefully finished by 2019. It's more complex than I showed it to you. Again, it's an international effort. I would like to use my final minute with the last part of our universe, which is dark energy. So dark energy actually makes up almost 70% of everything there is. What is dark energy and how do we know it exists? Again, we can't see it, we can't really feel it. Well, remember our universe. Here it is. 13.8 billion years after the Big Bang. We can measure the speed of acceleration of the universe, and we can actually see that it's accelerating in expansion. So the expansion of the universe is going faster and faster and faster. And if something is speeding up, there must be energy pushing it forward. And you can calculate, it's pretty easy actually, calculate the amount of energy necessary to speed up the acceleration of the universe in that matter. And this turns out to be equivalent to 70% of all the matter there is in our universe. And no, we have no idea what dark energy is or where it comes from. We really don't, and that's like an open field. Welcome to do research on that. The future of the universe actually is not pretty bright. Due to the accelerated expansion of the universe, in the very end, galaxies will be pulled apart so fast, faster than the speed of light actually, that light from our neighboring galaxy could not reach us anymore. Even faster, our solar system will be ripped apart because the space between Earth and Mars is expanding so fast that light from Mars cannot reach us anymore. we will be isolated. The bonds in our molecules, in our bodies, will be ripped apart because the space between carbon atoms and oxygen atoms will expand faster than the speed of light. So before we all evaporate in a few billion of years, remember the universe needs you in order to understand itself. So if you're interested in any of the projects I showed you, just visit the different roosters of the LISA mission, of the LIGO Corporation, of the Dark Cosmos Alps experiments. There are so many different universities doing research on that, and they all need engineers and physicists and computer scientists and so on and so forth. If you have questions, email me or see me later on the speakers couch. Thank you very much. Have a great night.
Okay, thank you very much, Simon Barke. As he already mentioned, there will be a question round before Hall G. I would allow a question from the internet if there are any.
Yes, there's a question. It's about the detection of gravitational waves. If gravitational waves change space-time, does it not also change the detection device, so we wouldn't detect them at all? Why does it work?
Well, what basically happens is that the travel time of light from the beam splitter to the end mirror changes. And yes, everything in there changes. The entire device becomes longer and shorter, but that's exactly what we want to measure. We want to measure that the light bounce back and forth is now a little bit faster than in the other direction. So we compress the entire apparatus and stretch it when a gravitational wave passes through, but that's exactly the effect we are measuring.
Okay, that wraps it up for today. Give another warm round of applause for our speaker.